Hello class, welcome to subtopic 3.5, the circle, in its part number 2 and final. So today guys, we're gonna just come up with two formulas, one of which will be derived from this problem, and the other formula will be deduced or derived from this problem. What are these problems? It's the problem of finding the length of an arc intercepted by a central angle, and the other is finding the area of a circular sector enclosed by a central angle. By now, you know all of this terminology. You know what an arc is, what a central angle is. The only thing that you don't know at this point is what a circular sector is. So we need to first find out what we mean by this, a circular sector. So let me tell you. When you have a circle and its center, and you draw any central angle, which I'm about to do, there it is. Okay, you can see that this central angle, let's call it theta. This central angle encloses a portion of this whole circle, all of this portion, which I'm gonna shade, all of this portion. And this is what we know as a sector. All of this little, it's kind of like a slice of pizza, you know, when you, oops, when you cut out a pizza, a slice of pizza, I'm sorry, this is what is known as a sector of the whole circle. So it's the same here. Any central angle encloses a sector, a circular sector. And that's what it means. That's all this word means, sector. Okay, fine. So let's do this thing. So first, what is the length of an arc intercepted by a central angle? So for example, the question is this, guys. I'm gonna draw a central angle. This is the radius of the circle. This is also the radius of the circle. And this is my central angle, which I'm gonna call theta. Okay, fine. So basically, this central angle theta cuts or intercepts an arc, which is all of this part of the circumference, and I'm gonna call it S. I'm gonna call S to the length of this arc, the length of this arc, which is intercepted by this particular central angle. How can I find S if I know this angle in radians? In radians. I'm gonna say that one more time. All of the analysis that we are doing right now is supposing that the angles are given in radians, not degrees, radians. So how can I find S if I know the angle theta and if I know the radius? Well, it's quite simple. I'm gonna use the theorem that we used the last class, and in here I'm gonna draw a radian. So this is radius. This is 1 radian. And if this is 1 radian, then by definition, this arc, the length of this arc should be also equal to the radius. Okay, fine. So we have two equal circles and we have these two angles. And if you remember, previously I told you that there's a theorem that says that the arcs are proportional to their central angles. And what that means is the following, that whatever ratio you have between theta and this other angle, whatever ratio they have in common, let's say that this angle is twice this one, then the arcs will also have the same ratio. That is, all of this arc S should also be twice this arc R. So this over this is equal to this over this. And that is always true. So let's write that down. So we have this angle which measures theta radians, over this angle, which measures just 1 radian. That's going to be equal to the arc S of length S, I mean, over the arc of length R. So there you have. Now we can simplify this equation a little bit. We can cancel radians and radians, and then theta over 1. Well, that's just theta, right? And we find that theta equals S over R. And that's how, guys, you can find, remember, what was the original question? If I know these two things, R and theta, can I find S? Yes, we have done it. Because now if I take this equation and I isolate S, I get the following. Theta times R. There you go. Which is usually written in this way. So whichever way you see this equation written, or this formula, it's obviously the same. Sometimes you're going to see it written like theta equals S over R. Sometimes you're going to see it written as S equals theta times R. They are the same equation. It's an equation that links or that connects this quantity, which is the central angle, the measure of the central angle in radians, and then the radius and the length of this arc. It's an equation that connects all of these three quantities. So it's a very important equation for us. I haven't seen whether this is in the booklet, in the IB booklet. I'm gonna look it up in a moment, and I'm gonna tell you tomorrow. Okay, so that solves this problem already. With this equation, we can find out uh, S if I know theta and R. Perfect. Let's continue. Now, the other problem that we want to face today is this. Let's find the area of a circular sector enclosed by a central angle. So, what I mean by that is this. Circle, center. I'm going to draw a central angle. This is the radius. This is another radius, of course. I'm going to label my central angle. I'm going to label it one more time, theta. And as we can see here, theta encloses this circular sector, which I am shading right now. So if I know theta, and if I know the radius r, can I find the area of this whole sector, which I'm going to represent by a sub theta? What I mean by this notation is the area enclosed by theta. Can I find it? Yes, we can. And we're gonna use a theorem very similar to the one before, to the one that says that arcs are proportional to the angles. It's extremely similar. What this theorem says is the following. If you have two equal circles and you draw two central angles, like we have already one here, and let me draw another one over here. And let's call this other angle, let's call it alpha. So alpha clearly also encloses its own sector, okay? And let me call this sector, well, let me call the area of this sector A sub alpha, A sub theta, A sub alpha. And basically this theorem tells you this, guys, that also the areas of sectors are proportional to their central angles. And what that means is this. If theta is twice alpha, then the area of the sector enclosed by theta, which is all of this stuff, will also be twice all of this stuff. You see? Or any other ratio. If theta happens to be 3 times as large as alpha, then the area of this sector will be 3 times as large as this sector. You see how it works? In other words, theta over alpha, the ratio of the angles, is going to be the same as the ratio of the areas. So if you notice, it's pretty much the same thing as the theorem before, but now with areas of sectors. That's how it works. So how can I use this theorem in solving this particular problem? We can do this. I'm going to leave this diagram as it is. I want to find the area of this sector enclosed by theta. And in here, I'm going to create an equal circle equal to this in size. And what I'm going to draw in here is uh, an angle of 90 degrees. Okay, this is an angle of 90 degrees, but I'm going to express it in radians, because remember, all the analysis that we should do here should be expressed with central angles measured in radians. So 90 degrees, this is 90 degrees. How do I express this in radians? We go back to the formula that we just found, which says the following. 1 radian equals 180 degrees over pi. And if I want to know what is the conversion of 90 degrees into radians, all I can do is take this equivalence, multiply both sides by pi. So we get pi radians equals 180 degrees, and then we divide both sides over 2. Pi over 2 radians will be equal to 90 degrees. Therefore, 90 degrees is equal to pi over 2 radians. And I can write that down in here. Pi over 2 radians. This central angle measures pi over 2 radians. Perfect. Now, since this is a quarter of a full circle, then what is the area of this sector, guys? Do we know it? Can we know it? This is just a quarter of the area of the full circle. So it's very simple to find the area of this quarter of a circle. If I know that the area of the whole circle is equal to pi r squared, this is the area of the full circle, as you may know by now. You should know this, guys. Then 1/4 is simply pi r squared over 4, right? And therefore, well, let me put it right here. This area from this sector measures pi r squared over 4. And now we have all the ingredients to solve our problem. What we can do is use the previously theorem that I showed you, and therefore say the following. This central angle over this central angle, the ratio of this angle to this angle, theta radians over pi over 2 radians, has to be equal to the ratio of this particular area, a sub theta, over this area of this quarter of a circle, which is this, pi r squared over 4. Okay, and the rest of the work, you're going to do it on your own. I want you to take this equation and isolate this, which is what we want to know. Isolate this, and you will tell me, and simplify as much as possible. Okay, remember, keep pi in its symbol. Do not approximate pi to 3 point whatever. No, keep pi as itself, and tell me what you get once you have isolated a sub theta equals something. Let's stop right here. That's enough. Thank you, guys.